Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe. Lecture 14, Ratio and Proportion. One day I walk outside to check the mail. I noticed the little girls that live next door were having a lemonade stand. They're having a lemonade sale. So I walked over and I asked, how much for a cup of lemonade? And they said 25 cents. And I thought about that. It seemed a little cheap to me. So I asked, well, how much does the bottle of lemonade cost that you made this lemonade from? And they said, oh, it was $4.50. And I said, and how many cups can you get out of one of those? And they said 15. And immediately it occurred to me that they were undercharging. So they're actually losing money. I think they were trying to raise money for a school field trip of some kind. And here they are, they're losing like a nickel for every cup of lemonade they sell. So ratio and proportion is actually important, and that's what we're going to talk about today. So, of course, the first question you're asking is, what is a ratio? A ratio is a comparison of two quantities using division. Now, there are two ways to write this. So, for example, if you were in a classroom where there were 3 girls for every 2 boys, the ratio of girls to boys would be written as 3 to 2. Now, this is a common way to write it, but I don't like it. It's hard to work with. I think the better way to write this is as a fraction. So another way to write that is 3 over 2. Now, if you want to keep track of units, you can put a little bracket like this, and you can write girls over boys. And that will remind you what the units are. So that is what a ratio is. Now, there's many different ratios we can make. For example, 3 girls for every 2 boys. You could also write something in terms of the number of girls per total number of students. So, for example, if all we had was 3 girls and 2 boys in the class, you would have 5 total students. So you could write 3 over 5 as the ratio of girls to students. Proportion is an equation that says 2 ratios are equal to each other. So, for example, the ratio of 3 to 4 is equal to the ratio of 6 to 8. Is that obvious to everyone? How do I know that that's the case? Well, for starters, ratios can be simplified in much the same way that fractions can be simplified. And in fact, they can be simplified exactly as fractions can be simplified. So we divide both the numerator and denominator by the greatest common divisor, and you will have a reduced ratio. So 6 and 8, they both share have a greatest common divisor of 2. So I can divide by that. 6 divided by 2 is 3, and 8 divided by 2 is 4, and so you see that they are in fact the same. Another trick from fractions that we can use when considering whether something is proportional to another thing is the trick of cross multiplication. So cross multiplying, what would we get? We would get 8 times 3 equals 6 times 4. Does everyone remember that, cross multiplication? So if these are in proportion to one another, then this will also be true. So what is 8 times 3?
24.
24. And is that equal to 6 times 4? What is 6 times 4?
24.
Also 24. So we see that it is in proportion. So that's a way to test proportionality. Once when I was in Washington, D.C., I was taking a tour of one of these historical buildings. I forget exactly which one it was, but the tour guide had mentioned that the proportions of the building, right, where it was designed according to the golden ratio. Has anyone ever heard of the golden ratio? It's supposed to be this ratio of proportion that gives the most pleasing or most beautiful presentation of something. The ratio is 1 to 1.618. Now, the building in question, if I remember correctly, 50 meters wide and 80.9 meters tall. So 50 meters, 80.9 meters. So the question is, was the tour guide right? Was this in fact designed using the golden ratio? So how would we figure that out? Well, we have to see if 1 to 1.618 is proportional to 50 to 80.9, or 80.9 to 50 rather. So we would write 80.9 over 50 is equal to 1.618 over 1. So let's cross multiply and see if it is in proportion. So 1 times 80.9, is that equal to 1.618 times 50? Well, 1 times 80.9 is easy. That's just 80.9. What about 1.618 times 50? Well, we can do that because we know how to multiply decimals, don't we? 1.618 times 50. We'll have a whole string of zeros, so we can kind of ignore that. And then we'll start with this 5 in the tens place. So I'll add a 0 here because we're in the tens place. What is 8 times 5?
40.
40. Carry the 4. 5 times 1 is 5, plus 4 is 9. 5 times 6? 30. Carry the 3. 5 times 1 is 5, plus 3 is 8. I have 1, 2, 3 digits behind the decimal point. 1, 2, 3. There we go. 80.9. So was this building in proportion to the golden ratio? Yes, it was. So the tour guide was telling the truth, huh? So let me give you one to try. Consider a room which is 16 meters wide. All right, sorry, long. And 10 meters wide. So the question is this in proportion to the golden ratio? So pause the video, try that at home, come back when you have your answer. Okay, so let's set this up. Is 16 over 10 equal to 1.618 over 1? Now, keep in mind that you only need this to be approximately true, okay? And so in this case, you're going to see that it's not exactly equal, but it's close enough to say, yes, I think this was a room that was constructed according to the golden ratio. So let's cross multiply. We have 1 times 16 on the left and 1.618 times 10 on the right. Now let's put to practice our knowledge of multiplying by 10. We know that if we multiply a decimal by 10, we need to move the decimal point 1 to the right, yes? So on the right-hand side, we have not 1.6, but 16.18. That's what 1.618 times 10 is. On the left-hand side, 1 times 16 is just 16. And so we see that to a pretty close approximation, this is, in fact, proportion. Well, this is, in fact, proportional. So I would say, yes, this room does adhere to the standard of the golden ratio. Does that make sense? Good. So when I got into model rocketry, I built a replica of a V2 rocket. And I wanted to know how this compared to the original. So this rocket is about half a meter long. And the original V2 rocket was 14 meters tall. So one of the common features that people do when designing things is they talk about a scaling factor. And so what we want to do is figure out what is the scaling factor by which this model was built. So what we want to do is we want to look at the original to model ratio. So the original was 14 meters, and the model was half of a meter. So what I want to do is I want to get this into units of some number per unit quantity. So I'm going to actually do this division to see what this ratio is in terms of 1. So I've got basically 14 over 0.5 equals some number, question mark, to 1. And we call this a scaling factor. So I can simply divide 0.5 into 14. That will give me 1 in the denominator, right? So we'll do that division here. 0.5 divided into 14.0, let's say. Well, remember, we can't just divide something with a decimal, so we have to move the decimal point 1 to the right. So I'll have to move this decimal point right here. And then move this decimal point here, but we'll just leave it out. So how many 5s go into 140? Well, how many 5s go into 14? You can almost get 3, but not quite. So we'll write that as 2. And 14 minus 10 is 4. Drop down the next digit. How many 5s go into 40? 8. 8 times 5 is 40, so that leaves us a remainder of 0. So we see that the scaling factor here is 28 to 1. I want to show you another model rocket, and if we use the same scaling factor, I don't think this will fit into the frame of the camera, but just for reference, it's probably a little less than, it's somewhere between 1.5 and 2 meters tall. Oh wait, I shouldn't have erased that. Scale 28 to 1. So what I'd like to do now is consider what would the actual size of that rocket be if we had the same scale factor that we did for the V2. So just to remind you, let's assume the model rocket is 1.5 meters tall. Using a scaling factor of 28 to 1, let's calculate what the actual size of the real rocket would be, given that scaling factor. So go ahead and pause the video and try that now. So we want to know what the real rocket size is when the model size is 1.5, and this should be in proportion to 28 to 1. So cross multiplying, we get 1 times the real size on the left is equal to 28 times 1.5 on the right. So all we need to do now is multiply these two numbers, but there's a decimal point, so let's take care of that. 28 times 1.5, 5 times 8 is 40, carry the 4, 5 times 2 is 10, plus 4 is 14. Drop down a 0 because the 1 is in the tens place. 1 times 8 is 8. 1 times 2 is 2. Add it all up. 0 plus 0, 0. 8 plus 4 is 12. We carry the 1. Now we have 2 plus 2 is 4. And there's 1 digit behind the decimal point. So we insert that right there. And so we get that our real size is 42 meters, which is pretty big. I think by comparison, Elon Musk's Starship, I think is what it's called, is about 120 meters tall. Everyone do well on that? Okay. Okay, another example of the use of ratio and proportion would be in cooking. So just imagine if you had a recipe for, say, cookies, and it called for, a teaspoon of sugar or something, or excuse me, a teaspoon of salt, which often is the case in things like cookies. I don't know why they put salt in cookies, but there's always like a little bit in there. And you were going to have to bump that recipe up for a larger batch. Maybe you had a recipe that would make, a certain number of cookies, and you needed to make a much larger version of that, right? If you were to not handle the scaling properly, then you might put too much salt in. And so that, a teaspoon of salt would turn into some really salty cookies, you see. That could be bad. So let's try an example along those lines. Let's say that a cookie recipe had a ratio of cups of flour to number of cookies, let's say, is 2 to 12. And so the question is, what if I wanted to make 30 cookies? If I needed 30 cookies, how much flour do I need? So we know that 2 over 12, that's cups of flour to 12 cookies, must be equal to some quantity, I'm going to use a question mark again, some quantity of flour for 30 cookies. Now I'm going to do something it's kind of a halfway between cross multiplication. It's just partly cross multiplying. I'm going to cross multiply, but only with the 30. I'm going to leave the 12 here. Instead of multiplying 12 times the unknown quantity, I'll just leave it right here. So this means that the question mark, the number of cups of flour, I guess I could write that in. Number of cups of flour is equal to 30 times 2 divided by 12. So the first thing we can do, of course, we can simplify this fraction because we see that 12 is the same thing as 6 times 2. And so the 2 in the numerator and the 2 in the denominator would cancel. And so this would be the same thing as 30 times 1 over 6. That's the symbol for ditto. It means copy whatever was above, okay? But 30 times 1 over 6 is the same thing as 30 divided by 6. And what is 30 divided by 6?
5.
5. So this says that 5 is equal to the number of cups of flour that we need to make 30 cookies. Now let me give you one to try. Let's say that you were supposed to make a fruit salad, and it was specified that the ratio of bananas to strawberries was 1 to 3. So the ratio of bananas to strawberries for this particular fruit salad is 1 to 3. Now let's assume that I happen to have 4 bananas on hand, and I want to use all of it in a fruit salad. So I want to determine how many strawberries am I going to need to add to these 4 bananas such that I have a fruit salad in proportion to the recipe. So go ahead and pause the video, try that one at home, come back when you have your answer. We could write this problem as 1 over 3 is equal to 4 over strawberries. But let me tell you, it's fine to use exactly the reciprocal of both of these. It's also true. If this is true, then it's also true that 3 over 1 is equal to strawberries over 4. Now, why would I want to do that? Well, because I have strawberries in the numerator. I can use the same trick that I did before. I can multiply both sides by 4, and I'll have strawberries all by itself. I say strawberries equals, and I'll have my answer, yes? So that's why I did that. So if I follow through with that, this means that strawberries, or the number of strawberries, is equal to 3 over 1 times 4. That's just multiplying both sides by 4. Well, 3 over 1, that's just 3. 3 times 4, that's just 12. So I need 12 strawberries to make a fruit salad in that proportion of 1 banana to 3 strawberries if I have on hand 4 bananas that I'm going to use in the recipe. Okay, now I don't know if you've noticed it or not, but what we're doing here is we're actually doing a little bit of algebra. Let me kind of formalize it a little bit differently so you'll see what I'm talking about. Let's say that I drive 180 miles in a time of 3 hours. So my miles to hours ratio is 180 to 3. You might say, well, I can take that and I can divide the number of miles that I've driven by the time it took me to drive. And if I put that into, if I make the denominator 1, then I now know how many miles per hour I'm driving. This is a very common thing. That's called your speed. So 180 miles divided by 3 hours is the same thing. Well, how many 3's go into 180? Well, we can divide that out. 3 into 180. 3 goes into 18 6 times. 6 times 3 is 18. 18 minus 18 is 0. Drop down to 0. How many 3's go into 0? 0. That gives me an answer of 60. And the units here are miles per hour. If I go 180 miles in 3 hours, how far will I go in 5 hours? This is a proportion statement. 180 to 3 is equal to x to 5, where 5 is the hours. X we call a variable. It is a letter that we use to hold a quantity, a number. Why we use x, y, and z in algebra predominantly, I'm not sure. It just the last few letters of the alphabet maybe. But it's very common in algebra to use x as the variable for the unknown quantity. And so that's what we've done here. So in algebra, we would say we want to solve for x, but you can see we've already kind of been doing that. It's that partial cross multiplication that we talked about. If I cross multiply, I'd have 180 times 5 equals x times 3. But if I just do part of it, if I just multiply both sides by 5, then I'll have x all by itself on one side of the equation. You see? So I've solved for x, as they say. And that is the objective when you're solving an equation in algebra. You want to get the unknown variable all by itself on one side of the equal sign, because then you've defined it. You said what it's equal to. But this logic of, well, can I multiply by 5? Well, of course I can. If I do something on the right-hand side, like multiply times 5, subtract 1, divide by 3, whatever it is I do, as long as I do it on the other side of the equation as well, it's perfectly fine. Because imagine that x was just equal to 1. If I multiply both sides of the equation, I do 5 times x is equal to 1 times 5. That gives me what? 5x equals 5. Well, if x equals 1, then 5x equals 5, right? So, solving for x, we multiply both sides of the equation by 5. Doing so on the right basically cancels the 5 in the denominator through the cancellation or the key fraction rule. And that gives me x all by itself over here on the other side of the equation. So I have that x is equal to 5 times 180 divided by 3. We already know what 180 divided by 3 is. We calculated that up here when we reduced this ratio, 180 over 3, and we turned it into 60 over 1, or just 60. So we can replace 180 over 3 with 60, and we get that x is equal to 60 times 5. Well, what is 6 times 5?
30.
30. So if 6 times 5 is 30, then 60 times 5 must be
300.
300. So this says that x is equal to 300. Notice how I switched which side x was on? That's perfectly fine. You can do that at will, and it doesn't change anything. 300 equals x is the same thing as x equals 300. So see, you've done some algebra. Is that cool? No? What about you? Think it's cool?
Sort of.
Sort of? Okay. All right, let me give you one to try. Instead of 180 miles in 3 hours, what if I had 300 miles in 6 hours was my ratio? How far would you travel after only 2 hours? So go ahead and solve that algebraic equation, or proportionality if that makes you feel better. Now, pause the video, come back when you have your answer. Okay, same as before, we'll just multiply both sides by 2. Multiplying on the right by 2 will basically cancel this 2 here in the denominator, and multiplying on the left by 2, we have 300 times 2 divided by 6. Perhaps the easiest way to do this is to recognize that 2 times 300, since 2 times 3 is 6, 2 times 300 would be 600. And so this would give us that x is equal to 600 over 6. And can anyone tell me how many times 6 goes into 600?
100.
100 times, right? So that is equal to 100. So that says that in 2 hours you would travel 100 miles. Another really useful aspect of ratio and proportion is unit conversion. So for example, let's say we wanted to convert miles into kilometers. Because in the United States we use miles for units of distance, and in, well, pretty much everywhere else in the world they use kilometers. So what is the scaling factor for that? What is the conversion factor for that? Well, there are 1.6 kilometers to 1 mile. So if I want to know what is 2 kilometers in miles, how would I set that up? You say, well, x miles is to 2 kilometers would be equal to this scaling factor. So we need kilometers in the denominator, 1.6, and 1 up here. So we'll multiply both sides by 2 to solve for x. We'll get that x is equal to 2 divided by 1.6. So that means we have to divide 1.6 into 2, which means the same thing as dividing 16 into 20. 16 will go into 20 one time, leaving a remainder of 4. Drop down the next digit. How many times does 16 go into 40? Well, I think we can get it in there 2 times. 16 times 2 is 32. That leaves a remainder of 8. Drop down another 0. How many times does 16 go into 80? Well, 16 times 5 that's the same thing as half of 160, which is, of course, 80. So we can get 5 16s into 80 with remainder of 0. So this tells us that 2 kilometers in miles is equal to 1.25 miles. So related to these units in unit conversions would be something like the following. 60 miles per hour. What is that in, say, miles per second? Well, 60 miles per hour, it's the unit of hours that we need to change to seconds. Let me show you how we do these kind of conversions. And this is the trick. Miles over hours times hours over minutes times minutes over seconds. Do you see what's going on here? I've set up these units such that the hours will cancel, the minutes will cancel, and I'll be left with miles in the numerator and seconds in the denominator. Okay, so what we want to do to solve a 60 miles per hour equals x miles per second is plug in numbers for each of these. So how many miles per hour? We know that's 60. How many hours per minute? Well, how many hours are there in 1 minute? Well, there's 1 hour over 60 minutes. Yes? How many minutes per second? Well, there's 1 minute over 60 seconds. So if I multiply the denominators of these two fractions, the rule for multiplying fractions, right, is you multiply the numerator, so we have 1 times 1, and we multiply the denominators, 60 times 60. Well, 6 times 6 is 36. So what do you expect 60 times 60 to be? Because here we've got another 10 by 10. What is 10 by 10?
100.
100. What is 36 times 100? 3,600, right? Or 3,600. So this is the same thing as 60 times 1 over 3,600. Now at this point you've got a choice, because this is the same thing as 60 divided by 3,600, but it's also kind of a fraction, right? Because we can move the 60 into the numerator here. So we have 60 over 3,600. We know that 3,600 is just 60 times 60, right? So we could rewrite this. 60 over 3,600 is equal to 60 over 60 times 60. We see the 60s will cancel, and we're left with 1 over 60. And now to finish it up, we would have to divide 60 into 1. 60 divides into 1.0. Well, it goes 0 times into 1. It also goes 0 times into 10, right? How many times does it go into 100? Well, 1 time. 1 times 60 is 60. 100 minus 60 is 40. Drop down another digit, another 0. How many 60s go into 400? What would 60 times 2 be? 120. If we double 120, we get 240. What about 60 times 5? Well, that's half of 600. That's 300. So we're getting closer. What about 60 times 6? That's 36. 360. And 60 times 7 would be, 6 times 7 is 42. That's 420. So we've gone over, so we can get 6. 6 times 60 is 360. And 400 minus 360 is 40. And we see we've got one of those recurring loops again. I could drop down another 0, and I'd be dividing 60 into 400 again, wouldn't I? So I'll just put a little bar over the 6 to mean that it repeats forever. So 60 miles per hour in miles per second is 0.016 repeating miles per second. A very small number, which is probably why we use miles per hour instead of miles per second. Yes? All right, let's finish up by reconsidering the problem that we saw at the beginning of the lecture with a lemonade stand. So $4.50 worth of lemonade to 15 cups. So it's 4.5 to 15 is our ratio, and we want to know what is the cost for 1 cup. Well, that's just a simple reduction of the fraction, right? So we can write 4.5 over 15, and we want to know how many dollars for just 1 cup. Well, multiplying both sides by 1 just gets rid of the 1, and so the cost of 1 cup is going to be 4.5 divided by 15. So we'll have to divide 15 into 4.5 15 goes into 4 0 times. 15 goes into 45. How many times does that go? Well, 15 times 2 is 30. 15 times 3, who can tell me 15 times 3? 45. 3. 45, leaving me a remainder of 0, which means that X, the cost per cup, is equal to 0.3, and that's dollars. How many cents is $0.3?
Like 33.
It's 30 cents. $0.3 is 30 cents. So if they're selling it for 25 cents a cup, you see they're losing a nickel every time they sell a cup of lemonade. So they might want to adjust their prices so they can make some money, maybe 50 cents for a cup. Yeah, something like that. Okay, that's all I have on ratio and proportion. The problems, I think, in the homework you'll find fun and interesting. At least I hope so. Are there any questions?
No.
Okay, well then I will see you next time.